Video 5 if you need it and you missed class. We're going to be proving our quads on a plane. And so we're going to start off with the first problem that we left off with in the previous lecture, in the previous video, that if we had any kind of just random quadrilateral and we connected together the four midpoints of those four random sides, that this makes a special kind of quadrilateral. And so I've got the same stuff that we ended with in the last video. I've already got kind of set up here. Again, we're going to be focusing on these four midpoints. Now, the math here is a little bit different because, again, we're not dealing with actual numbers here. We're dealing with nothing but variables. So in the video, I'm going to skip over a lot of the kind of slow and tedious math part of this and really just dive into what we've got going on. So let me just get rid of everything else here and let's focus primarily just on our quadrilateral we created by the midpoints. Now this is a really good chapter review type question because back in the day, at the very beginning of this chapter, I gave you guys 4 numerical points and I said, I want you guys to do some math with these 4 points and I want you to prove to me that the shape you think this is really is that shape based on the math. And you guys, once upon a time, had to calculate 4 distances and 4 slopes. And based on those distances and those slopes, you would tell me what shape that meets the particular criteria for the shape you say the answer is. We're going to have to do the same thing, okay? But the math is definitely going to be much more algebraic than it is just simply arithmetic. So here's what I'm going to do. I'm going to show you what the math looks like one time for one set of sides. And then we're not going to worry about the math for the others. I'll just give you what all the other values are. So first thing I need to call these points some particular names. So let's call them W, X, Y, and Z. And I'm going to work with, let's say, this side over here. So whenever we set these up, now let's do X minus W. Whenever we set these up to calculate the distances and the slopes, what we did was we subtracted our coordinates. So let me get these set up here. We're going to subtract away, let's say, W. It's half of B, comma, half of C. Now, if I subtract my x coordinates, initially, when you look at this, there doesn't really look like anything's going to be able to simplify. But B plus D divided by 2, that's really half of B plus half of D. And if I subtract 1/2 B plus 1/2 D minus half of B, well, this half of B and that half of B is going to cancel, and I'm going to be left with half of D. And the same thing's going to happen in the y coordinate. This C over 2 is really 1/2 C. So this part's going to cancel out with that, and I'll be left with this E over 2, or 1/2 of E. Now these two values represented two things for us in terms of distance and slope. These represented the A and B of the Pythagorean theorem so that we could calculate the distance, but they also represented the run and the rise for the slope. So we use these numbers in two different ways. So now if I were to consider the slope of Wx, and I did the rise, which is half of E, over the run, which is half of D. And the thing I notice here is that both these have a half, and they will cancel out. So E over D, I don't know what that simplifies to be. So this has a slope of E over D. Now the distance of Wx, we need to take the square root of our a squared plus b squared values because this represents our c value. So we're going to have to square our two quantities, and since there's two values here, we're going to have to square the whole quantity plus the whole quantity 1/2 e. We could simplify this up just a little bit, but it's really going to be too much of a hassle. Not really hassle, but it's really not needed that we need to go that far. So this is half of d squared plus half of e squared. That's what the math's going to look like. Now imagine doing that 3 more times for these 3 other sides, and it gets a little heavy, okay? Which is why I'm not going to have this type of question on, say, a quiz or a test. But just to make this go by a lot faster, I'm going to tell you that the slope over here for this side is also e over d. And the distance of this side is also quantity 1/2 d squared plus 1/2 e squared. So the math is telling us that these two sides are parallel because they have equal slopes. And these two sides are congruent in length because they end up with the same distances algebraically. Now the other two sides, this has a slope, once everything simplifies out, is c over the quantity, c over all of b minus a, and the distance, again, it's going to be ugly. It's half of b minus half of a quantity squared plus quantity half of c squared. And for the fourth side, I get the same two values as I did for its opposite side. Which again tells me since the slopes are equal, these two sides are parallel, and they're also of congruent length. Now, if we know that both sets of opposite sides are parallel, this thing is at least a parallelogram. But rectangles, rhombuses, and squares are also considered parallelograms. So we're going to have to maybe try to figure out exactly what type of parallelogram this is. Now consider this. If this is the length of this side and this is the length of the side that's right next to it, those don't look anything alike. I don't know what relationship A, B, and C has to D and E, so I'm pretty much assuming that these are of different value. Now they might be the same if I knew something special was going on with A, B, C, D, and E's variables. So this thing's not a square and it's not a rhombus, because I'm pretty sure not all four sides are the same, which leaves me with the rectangle option. And now I need to know, does this thing really have 90-degree angles? So the first thing I would look at would be the slopes. And so I need to look at adjacent slopes. So this side and this side, they're adjacent to each other. And if these two slopes are really perpendicular and make a 90-degree angle here, then their slopes would be negative reciprocals. And the negative reciprocal slope of E over D would be negative D over E. And is negative d over e the same as c over b minus a? I really don't think so. So I'm going to say with pretty good certainty here, these are not perpendicular slopes. So there are no 90-degree angles here. Therefore, if not all four sides are congruent and not all four angles are right angles, but I do know that the opposite sides are parallel, this thing is just a plain old parallelogram. Now again, that's a lot of extra work you're not going to have to do on a quiz or test, but it's a pretty amazing thing. You connect together the midpoints of any four sides of any quadrilateral, and it makes, I'll tell you this, at least a parallelogram. Depending on what your initial shape is, it might be a rectangle, rhombus, or square. But those are all at least parallelograms. Next problem we're going to look at, we're going to prove that the diagonals are perpendicular in this square. This was one of the problems that we looked at in the last video. So let me rewrite the coordinates that we came up with here. And if the diagonals are perpendicular, then we're going to have to calculate some slopes of these diagonals. And we're only going to have to calculate two slopes. We have to calculate the slope of this diagonal and the slope of this diagonal. And if the slopes are perpendicular, then they should be negative reciprocals of each other. And if they are, therefore they are perpendicular. So again, let's give these guys some names. Let's call this W, X, Y, and Z. And then let's do this red diagonal here. Let's do the slope of XZ. So we're going to need to subtract our points. So let's take X and let's subtract away Z. Now this is going to be a lot of algebra in here because we don't have any numbers to actually subtract, but variables. So negative a minus a is negative 2a, and then a minus a negative a is going to be positive 2a. So again, we got to remember that the first number represents the run, the second number the rise. So the slope of xz is the rise 2a over the run negative 2a. And then algebraically in this, the 2's can cancel, the a's can cancel, and the only thing we have left is this negative, and then when divisionally, if anything cancels out with each other, we just got a 1 left over. So the slope is -1 or -1/1 if you like. Now, let's figure out our slope for wy. W is -a over -a. Let's subtract away y, which is a. So -a minus an a is -2a. And we do the same math here. -a minus a is -2a. So then the slope of wy is -2a over -2a, and anything divided by itself in full here is +1. So +1 and -1, if we want to think about them as being 1 over 1s here, then -1 over 1 and +1 over 1 are negative reciprocals of each other. So then the last thing we can conclude here is since the slopes of the diagonals are negative reciprocals, then they are perpendicular. And we've proven this for every square because we didn't focus on a particular value of a. This is for all values of a. The third problem, we're going to prove that the diagonals of an isosceles trapezoid are congruent. Now, let's first come up with our coordinates here. This was b and c, and then up here we had a minus b, comma c. So in this problem, we're going to focus on length. We need to calculate the length of two diagonals. So we're still going to start out the same way. We need to subtract our coordinates to get the differences in the x and y's, but then we're not going to necessarily focus on slopes. So let's again give this w, x, y, and z. And let's start with x and z here. So if I took x, which is b comma c, and z, which is a comma 0, and so if I subtract b minus a, well, that's still just b minus a. And c minus 0 is c. And so these represented the a and the b values for the Pythagorean theorem. So the distance between x and z is the square root of our a squared plus b squared values, because this represents our c for the Pythagorean theorem. Okay? So we have to square root all this to get just c and not have c squared anymore. So we're going to take the quantity b minus a squared plus c squared. And we're just going to leave it at that. There's not much simplification we can do. And so now let's do the other diagonal. Let's take y and subtract away w. That'll be friendlier mathematically since we'll just subtract some zeros. And we'll get a minus b comma c. So the distance between w and y is the square root of these two things squared and added together. So we get a minus b squared plus c squared. Now, we needed to prove that these values are congruent of equal value. And they almost look like they're of congruent or equal value, but notice the b minus a and the a minus b. Those don't match up exactly the same. But what you need to consider is a minus b and b minus a really lead to the same number. One's positive, but the other's negative. And if we square those positive and negative numbers that are the same, we'll end up with the same value. So just consider this. If I had 6 minus 4 squared versus 4 minus 6 squared, 6 minus 4 is 2, 2 squared is 4, 4 minus 6 is negative 2, that same number, but the negative version, but negative 2 squared is still also 4. So these values, b minus a and a minus b, by themselves, they are different. But when you square them, they will end up being the same squared value. So they really are, in fact, congruent. And that'll be the only one thing that might look different, that you might not think that makes them equal. So as long as you're subtracting two variables and they're the same variables, it doesn't really matter which order you subtract them in, as long as you're squaring them right afterwards. And the last problem, we have a parallelogram, so let's come up with some coordinates here. So we're just going to use the same ones that we used in the previous video, previous lecture. This was a plus b comma c. And we want to prove that the diagonals bisect each other. Now, we would really need to show that these two pieces are congruent and these two pieces are congruent. So, man, we'd have to calculate 4 distances, which is really much more than we need to do. An easier route would be to consider this. Well, there we go. If I were to consider this diagonal that I'm highlighting in yellow, if it was being bisected, then we would hope this is the midpoint of this, that this diagonal is going to bisect this at this point right here. Okay, so we're going to hope that this is the midpoint of, and again, let's get some names here, W, X, Y, and Z. But hopefully this is the midpoint of W, Y. But if we also think about this on the flip side, what if we were looking at diagonal XZ and we needed to know that it was being cut in half? Well, where would it be cut in half at? Right at the middle point, at the midpoint. So this would need to be the midpoint of XZ. So what needs to be true about this one singular point? It needs to be the midpoint of both of these diagonals. So what we need to show is that the midpoint of this diagonal is the same midpoint of this diagonal. And if that's true, then that one point is the one point that's splitting up those two diagonals equally, and they're bisecting them. So now let's do the actual math here. So in the second example, we focused on just slopes. The third example, we focused on just lengths. Now we're going to focus on doing some math with midpoints. So let's start with this diagonal. The midpoint that we mentioned in the previous video or lecture, the midpoint was nothing more than the average of 2 points. But we had to take the average of the x-coordinates and the y-coordinates separately. So the x-coordinate of y is a plus b, and the x-coordinate of w is 0. So what is the average of a plus b and 0? Well, the midpoint, let's here, write this out. Midpoint of wy. We would take a plus b plus 0, which is going to do nothing, and we divide it by 2 because we have 2 x-coordinates. And that would be the x-coordinate of the midpoint. And then we got to figure out what is the average of the y-coordinates between c and 0. Well, c plus 0 is just c, and we would divide it by 2. So the midpoint of wy is this coordinate, a plus b divided by 2, comma, c divided by 2. So now let's work on the midpoint of xz. And again, we got to split this thing up between the x and y coordinates. So what is the average of the x coordinates between b and a? Well, it'd be b plus a or a plus b. Doesn't matter which way we add those. And we divide it by 2. And then what is the average of our y-coordinates between c and 0? Well, c plus 0 is c, and we divide it by 2. And so we do see that these two diagonals have the same midpoint. And if they have the same midpoint, they are bisecting each other. So that's where we're going to conclude here. Since the midpoints of the two diagonals are the same point, then the diagonals bisect each other. And that is all for this video 5.